Hello. In this lesson, we're going to talk about multiple slit interference. So how interference patterns occur with more than two slits and what we start observing and how that leads us into using diffraction grating. This is eventually going to lead us into using the diffraction grating to resolve different wavelengths. But for now, we're just going to focus on the behavior of light passing through more than two slits and then therefore getting to thousands of slits. So this is going to focus on just solving problems involving diffraction grating equation. We just have a warm-up. I'm going to pause this video. I think you should pause this video as well and do this practice, and in a few seconds come back and the solution will be shown. Okay, I've used the equation theta is equal to S over capital D, which is equal to lambda over little case d, which you can rearrange to find S is equal to lambda big case D over little case d, and this helps us determine the distance between the central max and the first max, or the first fringe, which is 0.002356. Now that's not 0.0047 because it's asking for the central max to the second fringe, which is, so that means that there is a path difference of two wavelengths. So I need to multiply this by 2 because I am under the assumption that S, the distance between maximums or fringes, should be equal, always under the angle of 10 degrees. This only works when theta is less than 10 degrees. It gets kind of, it changes when you get to further out. Now I could also see this as well if I changed my path difference from 1 lambda to 2 lambda, I would get the same answer. Showing the path difference to be 2 lambda, I can also even look even further and say, well, how about n lambda path difference? Well, I should get the same as long as the angle that we're looking at is less than 10 degrees. But really, that only happens in double slit and single slit experiments. Once we move on to adding more slits to our situation, the theta actually gets larger than 10 degrees, and we're not able to use the relationship theta. We have to start using sine. So as we move forward, we've already looked at our derivation of double slit, finding the distance between the central max and the first max when there's a path difference of 1 lambda. But now we're going to look at path differences of n lambda, just like I showed above, where this angle is going to be anywhere between 0 and 90 degrees. Of course, 90 being too far away from the screen and it won't show anything. Obviously, the angles can't be close to 90 because it's too far of a distance away, but we can at least, we do know that it's at least or maximum 90 degrees. Okay, well, the derivation of this really is the exact same thing as we did with double slit. We're just noticing that it's occurring at every single slit on this, what's called a diffraction grating. There are some mathematical errors going on here. We assume that these are all parallel to get the same triangle, and then since they're parallel, they're still hitting the same point, which we know that's a mathematical fallacy. That's wrong. No parallel lines do not intersect, but we are saying they're pretty darn parallel. And when I say that, it's just a it's kind of a negligible parallel, because all of these all should hit, when we're talking about this situation, all hit the same point. So since they're close enough to being parallel, we can make some approximations to our math, and it helps us out big time. Now, of course, like I said in class, if we were doing this at university level, high level university level, we would actually be taking more accurate calculations, more accurate analyses of this. But for right now, we make this assumption, and it lasts us pretty far. So we've already seen the single slit and the double slit pattern, the double slit pattern fitting inside of the single slit envelope. And as we add more slits, and we're really kind of adding like slit density, we start noticing different occurrences happening to our maximums, and we see things happening in between our maximums. So we need to give these labels. These are our primary. These are our primary maximums. Those are the ones we really pay attention to. But we also have these small little things. So let's make that a little bigger. Small little maximums that occur below, and those are our secondary maximums. And you'll notice, at least in these two situations, that the secondary maximums increase in number as we add more slits, but their intensity decreases. And we also notice that the primary maximums do get thinner, which means they get more defined. And as they get more defined, sometimes even more intense because we're adding more slits, more light passing through. So as we increase number of slits, two things occurs. And like I just said, I said that the primary maximums get thinner and more intense, whereas the secondary maximums, though they increase in number, their intensity decreases. And you'll notice that at some point in time they decrease so much to where they're not even visible, like in the 7-slit situation. And as we thin out our primary maximums, they get easier and easier to see or measure. So you'll notice up here, these are like harder to measure precisely, like measure the distance precisely. And as we add more and more slits, this is easier to measure precisely. And this becomes very important as we observe different wavelengths of light passing through the same diffraction grating, because we know that the angle that a wavelength diffracts through some slits is dependent on the actual value of the wavelength. So if we have different wavelengths passing through, we're going to see different intensities at different positions. And as the thinner they are, the more defined they will be, and the more we can separate them, and we can start resolving different wavelengths. Before we get there, though, we just need to let's look at the math and make sense of this. So the relationship that we see is n lambda equals d sine theta. This is no different than what we saw in the past of sine theta is equal to n lambda over d, except our n lambda is now our path difference, just like we did in the warm-up, where we have 0, 1, 2, 3 wavelengths path difference, giving us 3 maximums, 2 maximums for 1 maximum for constructive interference. And then why do we need to use theta? Because now angles are greater than 10 degrees. So none of this is different, except we do call n, and actually sometimes we do sometimes we'll also see it as m. It's just be annoying, but this is what's going to be called the order. But it really is the maximum number. Central max is 0, first max is n equals 1, n equals 2, n equals 3. And so forth, right? Dot, dot, dot. D is slit width. There's nothing different about that, except that a lot of times we will not be given the slit width. We'll be given how many slits there are in a given distance. So we need to find, this is also the distance between, and say this is or, distance between slits. And this will be useful when we get this like slit density. So the difference between distance between slits and lines per millimeter is this is how we will be given their distance between slits. How many lines are in a single millimeter. So in this example where we need to solve for D in order to solve a problem, they might say a diffraction grating has 3,000 lines per millimeter. Now they'll never actually ask you to calculate the distance between each slit, but you will need to do it implicitly. In this case, I'm asking you to do it though. So if we have 3,000 lines per millimeter, and I want to get distance between slits, well, distance between slits, even though it's meters, it's also like meters per line. That's kind of what it is. So let's actually take that right here. Distance between slits is the same as meters per line. So how do I get lines per millimeter and I convert it to meters per line? Well, I just need to rearrange. It's just an inversion and a conversion of millimeters to meters. So if I have 3,000 lines per meter, per millimeter. I'm going to take that and say, well, that's 1 millimeter over 3,000 lines, which is the same as 1 times 10 to the negative third meters divided by 3,000. And if you do this, you end up with 3.33 times 10 to the negative 7th meters. And that is my meters per line, which is the same thing as my D. Okay, now let's see how that helps us look at different wavelengths passing through diffraction grating. In this situation, we have an incident plane wave made up of red and blue light. Red and blue light having different wavelengths. And since we know that the sine of theta, or therefore like the theta, is dependent on the wavelength of light, we are going to see that red and blue don't hit at the same point because the angle is different as the theta changes. So as lambda increases, our theta is also going to increase as well. And so you can see this blue and red being separated by diffraction grating. So we need to find points on the screen for us to observe where is there red light, where is there blue light, and where is a specific wavelength. And so this helps us separate light into different bands or lines on this screen. You'll also notice that the distance between, let's say, the red and blue light at the first order, and you'll notice here this order, it has M instead of N. Like I said, sometimes they use M, sometimes they use N, and it even shows up in two equations where they actually mean the same thing. We'll get there, and I'll apologize again. But you'll notice this distance is smaller than this distance. And that has to do with the way that light is incident at an angle on a surface. So it's going to actually, the light here is actually going to be thicker than the red light observed here because it's being shown at a greater angle on a surface. And so just know that that can happen, and if a relationship shows up, you need to kind of discuss what happens between each orders. So you know as like the N increases or M increases, that the primary maximums will have a larger width. Oh, that's WIT. Now, as we do this with multiple light sources, or white light, I should say, multiple light wavelengths such as white light, we will be able to separate the white light into all of its different wavelengths. And where we have each maximum is getting wider, you'll notice the red light up here is wider than the red light down here, just like I was saying. And you'll notice that there's white light in the center because every single light is coming in and constructively interfering, producing white light, the sum of all of the lights. Now, we want to identify these orders and try to say how many orders can we or will we be able to observe on a screen. So first is to be aware of how we identify these orders. So 0th order, which is pretty much our central max. And then we have first order, second order, third order. You can see that they're actually getting further and further apart, as I said before. This is path difference of 1 wavelength, path difference of 2, path difference of 3, and so forth. We also know that it is symmetric on the other side. So first order, second order, third order. And how many orders can be observed on the screen, or what's the theoretical maximum angle that an order can be observed? Well, I know that if a light is shining out of this diffraction grating at this angle, or 90 degrees, it definitely cannot be observed. So it must be less than 90 degrees, or our theta must be less than 90 degrees. So when I set up the relationship of n lambda over d, which is equal to sine theta, I know that theta has a maximum of 90 degrees, so it must be less than, or sine of 90 is 1, so n lambda over d has to be less than 1. And so I can solve for n. I just get n is less than d over lambda. And whatever value I get, I know it must be less than that. So if I get like 2.7, then 2 must be my maximum order because it can never reach the third order. Now that's it. I've just got an example problem to kind of finalize today, where we have a diffraction grating having 600 lines per millimeter. It is illuminated with a parallel beam of monochromatic light, which is normal to the grating. This produces a second order maximum. So already got a second order maximum, 600 lines per millimeter. That is observed at 42.5 degrees from the central maximum. Calculate the wavelength of light and how many orders can be observed on this screen in particular. So let's first start by calculating the wavelength of light. We have an angle, which is equal to 42.5 degrees. We have N, or M, eventually we'll see it, is 2. And D is something we don't know, but because we have 600 lines per millimeter, so I need to rearrange that into meters per line, which is 1 times 10 to the negative third divided by 600. And I can solve for this using what sine of theta is equal to N lambda over D. Solving for my wavelength, which is, so this is D sine theta over N, and I'm going to pause this video and solve for this. So I get 5.63 times 10 to the negative 7th meters, which is 563 nanometers. And how many orders can be observed on the screen? So I know, again, sine of theta is really sine of 90 is equal to N lambda over D. And I could just solve for this, right? 1 is equal to N times 5.63 times 10 to the negative 7th divided by, oh, I actually didn't even do that one. This is 1.67 times 10 to the negative 6th. I get N is equal to 1.67 times 10 to the negative 6th divided by 5.63 times 10 to the negative 7th. I get 5. I get N is equal to 2.96. But really, N, should be less than that. Definitely cannot be greater than that. And so then I have a maximum of 2 orders. So whenever if I had like a diffraction grating right here, it would go central max, first max, second max, first max, second max, and that would be a total of 5 orders observed. Although we have a maximum of 2, as I said in class, this shows that there are 2 on one side, 2 on the other, plus the 0th order. So we have 5 orders observed, and that would be your order. That's how many orders that can be observed on the screen. All right, hope this helps. See you in class.